We've seen complex numbers briefly before when we're solving quadratic equations, but section 4.8 is all about expanding our knowledge of that and trying to use some complex numbers in some operations. So in our first example, when we're trying to just write the imaginary number in the first place, we're going to use our imaginary numbers, remember, when we're using any kind of negative inside our square root, so what we call a negative radicand. And if I want to separate this square root of negative 25 into the square root of the negative portion and just the square root of the 25, again, just because negative 1 times 25 gives us negative 25, the square root of negative 1 is where we're going to decide is that imaginary number I. So that's going to be the I portion of our answer. And square root of 25 is just going to make 5. So if I combine those together, I times 5. We really want to write the 5 in front just like a coefficient. But our imaginary unit is just going to be calling that 5i. Because again, we can use that square root of a negative just by making sure that we refer to that as an imaginary number. Much the same thing on the next two questions. We just want to make sure on something like part B, if I'm able to do something like simplify a square root, so square root of 12 contains that perfect square. 2 times 2 would give us 4, so 4 times 3 making 12. 2 rad 3 is how I can split up the 12, but I can still separate the imaginary portion as just I itself. And again, just like with our coefficients, and just like if I was an x, I would stick that I in front of the radical, but just 2i rad 3 is going to be my imaginary answer. And with our last example, not really anything we can do to simplify at all. So square root of 7 is still going to be square root of 7, but just to denote that that's going to be a negative square root, we're just going to use that I rad 7 instead. If you've read the blurb from up above, or again, also have some experience with this with earlier when we did quadratic equations, we know that we don't just need an imaginary portion. We could also combine a real and imaginary portion of our answer to create what we call a complex number, like our fixed example, 5 minus I. So we're asked to do two things. We're asked to graph and also find the absolute value of those complex numbers. In terms of the graph, we just want to treat this like our x and y coordinate system, with the x standing in for the real portion, and that would be the 5 portion of my answer. And then the imaginary portion, that just minus I, that's just going to be what we denote going on that vertical axis, which used to be our y-axis. So if I want to graph this imaginary number then, or a complex number rather, with 5 being the real portion and negative I, or just like a negative 1i, being my imaginary portion, we can treat this just like the x-coordinate is 5 and the y-coordinate is negative 1. I can just have it located at that point in my graph. So now if I'm trying to find the distance, or again, absolute value to go from that number, that would be the distance from 0 on our coordinate system. We can find that just like we find any other distance by using that distance formula. Except now it's going to be looking a little bit different. Instead of x and y, we're just going to have a and b. So the imaginary and real portion of my answer, or I guess kind of flipped around there, real and then imaginary. Which means if I want to find the absolute value of this, so the absolute value of that complex number, 5 minus I can take the square of the first term, so that's going to be 5 squared. And if I just have something like a negative I, we can imagine that to be like a negative 1 in front, so like negative 1i instead of just I by itself. So if I'm using that for my b portion, again, that's the imaginary portion of my answer, I can just simplify what I have inside of that square. So 25 from the 5 squared, negative 1 squared is just 1. So if I'm looking for, again, the distance from 0, or what we call the absolute value of that complex number, that's just going to come out as a square root of 26. We can do kind of the same thing on our next part of our answer, which is, again, just imaginary and no real portion. On the graph, I already have that pictured. Just the imaginary number just means it's going to be on my vertical axis, but it's not going to have any kind of left or right movement on that real axis. And if I want to find the distance, it's actually kind of easy enough from your graph to count the distance on this one. All we're really doing is going up 6, but if I want to use that same formula, absolute value of that complex number is going to be, again, just like using a distance formula, square root of a squared plus b squared, which again kind of comes from our Pythagorean theorem if we're thinking of that, just like how we found that first triangle. And since I don't have a real portion of my answer, I can just consider that portion 0. But if I square the imaginary portion, 6 squared, square root of 36 then just turns that number back into 6. So we can see again from our graph that the distance, or the absolute value of that complex number from 0 is just going to be 6. With our next example, we can get in some operations we can do with our complex numbers. So with our first two examples, we can find a sum or a difference. Again, sum or difference being adding or subtracting. And then we're just looking at what we have listed up above as combined like terms. Combined real parts and imaginary parts means if I have these real portions of my answer, 7 and negative 3, or my question rather, 7 plus negative 3, that's going to be the real portions. I can then also combine as like terms the imaginary portions, negative 2i. And you can also think of like a 1i or just positive I. As long as I combine those like terms separately, I'm just left with 4 from the real portion. I'm left with, it looks like it's just a negative 1 or just a minus I for the imaginary portion. That's going to be my sum, is just again treating those like terms. I can combine the real and the imaginary portions separately. If I was to subtract, so to find a difference on our next example, something I think is going to keep us consistent is if instead of we treating this like a subtraction problem, since we are going to be worried about, again, distributing that negative and thinking of these as like terms, I would rather treat this like an addition problem as long as I'm just changing the signs on that expression that's following my subtraction sign. So instead of saying 1 minus 3, we're going to get the same result by doing 1 plus a negative 3. And that's also going to keep this consistent. So rather than thinking of like minus a minus 2i, we know that two negative signs are going to cancel out, make that into a positive. So I thought of that as 5i plus 2i. Just with our last example, though, we want to combine our real portion and our imaginary portion separately. So if I get negative 2 from the real portion and 7i from the imaginary portion, that's going to be my complex solution. So now if I want to find a product or multiply complex numbers, a lot of this is going to depend on our multiplication skills with our binomials from earlier. In our first example, if I just have two, again, not necessarily a real portion, but just two imaginary numbers, 7i and 3i, I can multiply those together, 7 times 3 making 21, and I times I making I squared. A lot like how I'd get 7x times 3x is like 21x squared. Here, though, we know that I squared has itself meaning. Square root of I by itself is the square root of negative 1. So when I square that, every time I have an I squared, I'm just going to have a negative portion of my answer. So that's going to be a negative 1. So instead of saying 21 times negative 1, we actually could find the answer to this one just by simplifying that I squared. Again, now that we know that it's a negative, we're just going to change the sign of our answer, and that's just going to be a negative 21. So that concept comes into play in the next couple of examples too. First thing I'm looking at, if I'm looking at an example like B, is that I would need to do a box or a foiling distribution, some kind of method where I'm multiplying those two binomials together. I chose the box method, so just to show my work in this example, 2 minus 3i wrote across the top of my box, 4 plus 5i wrote down the side. And just like we do every other kind of box method, I'm going to multiply and form out each square. 2 times 4 to get 8, 4 times negative 3i, 5i times 2. And then as bottom right corner, kind of like in our last example that we saw, if I'm multiplying two imaginary numbers together, we do want to consider what's going to happen when I use that I squared. It's going to essentially just change the sign of my answer. So kind of like how last time we had a 21 but changed our final answer to a negative because we had I squared. Here, I still have my 3 squares that act just like as they would in every other question. But if I see something like negative 15 I squared, I know that negative 15 is going to be a negative, but that I squared is going to change that answer back to a positive because I squared by itself is going to be a negative 1. So negative 15 and negative 1 combine just to make that into a positive 15. From here, though, we're just doing the same thing we did in our last example. For example 3, we have two real portions. That's going to be 8 and 15. That combines to make 23 for our answer. And then with our imaginary portion, negative 12i and positive 10i, just like a lot of your other box questions, our diagonals we can also combine. That's where I'm going to get minus 2i for the imaginary portion of my answer. So C, we could approach the same way if we'd like, but this one also does have a shortcut if I recognize that these are two conjugates. If I know I'm just doing A plus B, A minus B type question, I know I could simplify that as what we call the difference of two squares. So in that portion, I'm just taking the first term from each binomial. That's negative 4. I'm taking the second term from each binomial. I know it's 5i. Again, a plus or minus just means that it fits our pattern. So I could box this out if I wanted to. But if I know that it fits my difference of two squares pattern, negative 4 squared is going to be a positive. But this is where I have to remember, if I square something like 5i, and if I get 25i squared, just like we saw from before, it's actually going to change the sign. So I actually need to think of this rather than a positive 25 instead of as a negative 25. Because again, we do have that I squared, which is going to change that sign. But since we have another negative, again, a squared minus b squared in that question, difference of two squares, I would eventually be subtracting that negative value anyway, so you can think of that as adding a positive. And 16 minus a negative 25 is just like saying 16 plus 25. That's where that answer of 41 is going to come from. So we've added, we've subtracted, we've multiplied. Let's see what happens now if I take a quotient, which is dividing two complex numbers. So a lot of this depends on how well we understood simplifying radical expressions from before, if I'm trying to do something like rationalize a denominator, because we're going to be doing the same thing here. Again, the instruction we have from above is to use a conjugate to simplify this kind of a quotient. And we know from a conjugate, we're going to be looking for the conjugate of the denominator of our fraction. So the conjugate, remember, is going to be using the same two terms, but if the first one was a sum, 3 plus 4i, now I want to be using a difference, 3 minus 4i. And just like with any other fraction, I can't multiply the top and the bottom separately. Don't want to change the value of that expression, so I have to multiply top and bottom, numerator and denominator, by that same expression. So across the top, you could multiply out in a box, you could use distribution. I'm going to use the foiling method. I'm going to kind of do this one in my head. Multiply the first terms together, I get 15. 5 times negative 4i, I get negative 20i. Negative 2i times 3, I get negative 6i. And then here's where we have to be careful. If I have a negative 2 times a negative 4, I would be getting positive 8. But remember, every time I have an I squared, which is I times I put together, that's going to change the sign again, so that's going to end up as a -8. Again, even though -2 times -4 would have been a positive, we do have to change that sign whenever we have I squared. So across the bottom, this is going to be, again, kind of like with my difference of two, or sorry, my sum and my difference. This is going to be a difference of two squares, so 3 times 3, I get 9. Again, we could multiply out for the middle terms, but if I know that I get a -12i and a +12i, those are going to cancel. I know that as a difference of two squares, this is going to be 9, and then minus 4i squared is going to be a -16. Remembering that 4 squared makes that a 16, but same as we saw from the numerator, I squared is going to change that back to a positive, or sorry, negative. Now I can actually look at simplifying each part of my fraction for my final answer. So simplifying across the top, 15 minus 8, combining those real portions, I get 7, minus 20, and then minus 6 more, I get minus 26, and that's going to be I for our imaginary portion. And then 9 minus -16, again, is like saying 9 plus 16. That's where I'm getting 25 from. We also want to make sure, just for our complex numbers, that we list this as a real and imaginary portion. So it does look about the same, but we want to make sure if I separate that into a 7 over 25 for the real portion of my answer and -26 over 25 for the imaginary portion, that's going to be how we look to simplify any complex number. So B is actually a little bit easier if I just have something like 6i. 6i, as we remember from before, we don't have to use a conjugate. We can just multiply by that term itself, much like when I'm trying to just simplify a square root by itself on the bottom of my fraction. But we do have to be careful here again. If I was to distribute across the top, I'm multiplying twice, and much like we've seen from before, -6i squared changes that into a +6 because I squared is going to change that sign. And we see the same thing across the bottom. 6 times 6 is 36, but since I'm using I times I and creating that I squared, I am going to be changing that sign. And instead of a +36, we'd be ending up with a negative. So here's where I just separate again into the real and the imaginary portions of my answer. It's a little bit out of order, but we're able to, again, just rearrange that. -6 over 36, I also want to simplify the fraction if I can. So I get -1/6 from the first portion. Remember that both of these would still be a negative because we use that denominator as negative for both. And yeah, it's just going to be a -24 over 36, which I can also use to simplify that fraction. So we do want to be careful that, again, as long as I'm able to simplify the bottom part of my fraction, I still don't want to keep those parts together if I'm trying to list a complex number as an answer. I need a real and imaginary portion that I can then list separately. As long as I can simplify both fractions, I can also simplify those separately. So now if I'm looking to factor, this is going to look a lot like factoring from our previous section. We can start same way as we always would by looking for any greatest common factors. Looks like 5 can be divided into both of those terms, so I want to divide that out first. And previously we'd done because we couldn't really list our answers as imaginary or complex numbers. But now if I have any kind of sum of two squares, so a difference of two squares, we'd have conjugates. But now with the sum of two squares, we'd be able to list them as conjugates, but they will be using a shortcut that uses an imaginary number. Because again, if I have a negative and I'm trying to use that I squared, that's how we're going to actually change that number to a +4. So this is just going to fit our pattern, x squared plus 4. Again, x squared minus 4 would just be a difference, a sum and a difference without using complex numbers. This is going to be similar. It's going to be x plus 2 and x minus 2, but if I want to create that second term to be positive, again, previously it'd be -4, but by doing I times I, using that imaginary term, we are going to be getting a +4, so that's where that x squared plus 4 comes from. And B is a little bit faster actually, so we're only just using that shortcut. We don't have to find any greatest common factor. Here I'm just using that same kind of pattern. If it's a sum of two squares, previously I wouldn't be able to factor it, but now we can say we can factor that out as the real and the imaginary portion. Since the square root of 81 is 9, I can say that's x plus 9i and x minus 9i. Again, -9 times 9 is -81, but by using I times I and creating that I squared, that is going to turn that back into a positive so that this is able to factor. So for example 7, you can see I already have my work there because, again, it does take a lot of writing every time we're using what we call this quadratic formula. So that's our Pop Goes the Weasel song, if you remember that one. But that means if I'm looking for solutions, we wouldn't be able to normally find solutions if it's not factorable, if I can't do something like find a real answer. But I could simplify this down using our quadratic formula. Again, if I'm able to get somewhere like here, I can see that that's going to contain an imaginary answer as long as that discriminant would be negative. I'm not going to have a real solution, but I will have a solution that we can say is imaginary. So you want to just make sure that when you do use that quadratic formula and you separate into a complex number, you can separate into a real and imaginary portion for your answer, with the imaginary portion just taking care of that negative inside the square root. So for part B, I did pretty much the same thing. Again, if I'm doing something like 16 minus 20 and getting -4 as a discriminant, not going to have a real answer, but we still want to simplify that as far as we can. 4 plus or minus 2y all over 2 means I could divide that separately. 4 over 2 and then 2 over 2 can simplify as just 2 plus or minus I rather. For that last section, it's a good idea if you guys want to try these individually, maybe look back to problems that are similar from above. I'm just going to show all of our solutions so that you could check your work and just double check. I would guess I'd see any kind of answers that you're getting wrong here. But again, we're doing something like simplifying radical from the first part of the video, using our operations to multiply or divide, and then we're going to finish by finding solutions.